Hello, hello everyone. My name is Utkarsh shastrakar, and today I will be giving you a review on the paper titled PV site suitability analysis using GI space spatial physical multi-criteria evaluation. This paper is written by Yasin Charabi and Adil Ghasli. This paper was published in 2011 and it is targeted at the search area of country of Oman. So before going to the details, I would like to brief through the introduction of the paper. So the introduction of the paper, in the introduction of the paper, we have realized that throughout the world, the investment in renewable energy is continually growing because with as the people are becoming more and more aware of the environment and its degradation and the energy crisis, the demand for energy is growing around the world. So it is seen that the countries that are suited in the tropical countries which receive which receive solar radiation quite constantly throughout the year are investing more in solar energy and green energies. So the introduction also makes some comparison between the conventional PV technology and the CSP technologies. So it is seen that the CSP technologies has been on a growth throughout the world compared to the conventional PV technologies. The conventional PV technologies are the photovoltaic technologies where we use solar panels or solar panels that are based on diodes which directly convert the radiation into electrical energy, whereas the CSP technology is a technology where there are mirrors that has mirrors and kind of lenses in combination that are set up in an area which focuses the radiation gathered at a central point. At the central point, there is a huge tower which is used to absorb the heat of the radiation, which uses some kind of substance which is vaporized, and then that vapors are used to boil the water, which in turn then is used to run the steam turbines. So in this image, you can see that all these dots are basically small mirrors which are focusing the radiation towards the tower, and then the heat is captured. So typically the temperature at the center uh, of such mirrors is around 550 degrees Celsius. It's quite high. Then in the introduction, we even have understood regarding the GIS technologies and how there are been different strategies and technologies being incorporated in the GIS. One such technology which has been incorporated from quite a long time are multi-criteria decision-making technologies, which help us to decide different factors affecting a major problem. Then it is seen in the introduction that the conventional photovoltaic technology is more suitable for arid countries, because if you can see in this image, that is a CFP technology, all these mirrors and lenses are polished surfaces are needed to be continuously cleaned and monitored with the help of fresh water, which is quite not available in arid countries. So in such regions, the conventional photovoltaic cells are more efficient if water is not available. Then at the end, we'll make mapping models to actually segregate the suitable areas and non-suitable areas. Then we have the overview of multi-criteria analysis. So basically, multi-criteria analysis is used to condense complex problems by considering the various criteria affecting the problem one by one. So it is a robust approach dealing with complex decisions. So in this paper, they have actually uh, we have considered OW and AHP algorithms. So these are two kinds of algorithms which have been considered in this paper, and these are the algorithms which have been incorporated in the GIS. For example, we are using they have used our GIS in this project, and at the end, they have actually used the AHP OWA as a combined algorithm, which is implemented using fuzzy quantifiers in the ArcGIS to actually create weights for all the different criteria which we have considered. And then some of the criteria which are considered are accessibility, then the accessibility to the electric grid, because if a electricity generation farm needs to pump the power into already existing grids. So if the grids are not are not near the plant, then there is the additional cost of transmission and creating the towers and the transmission lines. Then we have the application methodology for PV farm siting. So these are the basic steps or the criteria that are considered. So PV site suitability. The first one of the most major criteria that are considered are the radiation level. So you can see a map which gives us the long-term average photovoltaic power potential. So basically, it is a map which shows the average average solar radiation that is received by the Earth's surface over an area of time, or in this map, it is particularly annual. And then there is a selection of the criteria. So selection of criteria is actually we have to select different criteria are to be selected which actually affect our problem. So in this paper, the criteria that they are selected are accessibility to the site, then availability of solar radiation throughout the year, and then other criteria like availability of like topography, whether the terrain is flat or is sloping in nature. Then we have solar radiation topography, which we have discussed, and then the analysis tool. So the analysis tool, we have said that we have used OWA-AHP algorithms, which are incorporated in the GIS platform. And then the next step is generation of criteria weights. So once we decide the criterias, then we have to assign them weights so that when we create the final layer, so uh, so the criteria which affecting maximum to the problem has the maximum influence in the our layers as well. For example, the most major criteria affecting the study was solar radiation, available solar radiation. So while considering the criteria of solar radiation, it would be assigned high weightage, and the other subsequent layers will be assigned less weightages. Then we have study case implementation and result. So these are the steps, the process that is condensed into the 5 steps. The first step is to collect the georeference data. So all the data like maps, then outlines, then digital elevation models, solar radiation models are need to be downloaded from different sources, and the satellite data needs to be downloaded, and at the end it needs to be standardized. So the files that are vector files are converted into raster files, and then the pixel value they have selected is 40 meters. They have selected a pixel value of 40 meters because the digital elevation model they used was having the pixel size or cell size of 40 meters. So to maintain a standard pixel size throughout all the layers, they have used 40 meters as standard pixel size. Then we have the solar radiation analyst module. Then they have used the solar radiation analyst module of the ArcGIS to calculate the total solar radiation. So when the solar radiation data is downloaded, it is available in some kind of a wavelength. In terms like the satellite uses an instrument, and that instrument generates an image which needs to be converted into a comprehensible spatial layer. So that can be done with the help of solar radiation analyst module. So all that footprint of wavelength which is reflected, which is calculated by the uh, instrument on the satellite, is further converted into a comprehensible map. Then we have constraint layers. So the constraint layers are the basically layers which are further additional constraint on the ground level for these plants. For example, accessibility, then type of terrain. Then another major criteria they have considered is land accessibility. So considering we have to set up a solar plant, so it needs to be easily accessible by road, because first we have to transport all the equipment, and the installation cost will be very high if the site is not quite accessible. Then we have to even construct the roads till for the accessing the site, and again if it is in some secluded area, then the transmission costs are also very high. Then all the above layers were entered into Floa module, which were actually consider the layer as per their weight, and then generate a final layer, which we'll see ahead. Then we have the spatial distribution of annual solar radiation. So in this map, you can see the country of Oman. There are areas which are highlighted in red color. So the red color areas are the areas which receive a high concentration of solar energy compared annually. And then we can see that majority of the land is not does not actually receive a high amount of solar radiation. So, for example, the central part of the central Oman does not receive any radiation that could be exploited to generate electricity. The major areas receiving solar radiation is mountain ranges in Oman, and then some areas in the coastal regions. Then we have the constraint layer. So this is the constraint layer which actually is prepared using the digital elevation model. So you can see the exploitable area is quite high, just considering the considering the criteria of slope. So the yellow region, which is termed as exploitable, is usually the terrain that is flat or the terrain which has a slope less than 0.5 degrees. So we can use flat terrains to set up uh, electronic panels. So it's easy to set up electronic panels in flat terrain, and then the sloping areas which are in the which are in the slope gradient of 0.00 to 0.5 degrees can be used to set up panels which are facing towards the sun. So that is in considering the geographic location of Oman. So if they're facing towards the south, the slopes in the range of 0 to 0.5 degrees facing towards the south can be utilized to set up panels to exploit solar energy. Then we have the spatial distribution for distance to major roads. Now this is a layer which actually shows us the road network in Oman and the accessibility. So the red color regions are actual road, and as we go away from the roads, that is around a buffer of 0 to 65 kilometers around the major roads. So we can see the central Oman doesn't have uh, various roads. So it's actually an arid region with a kind of a desert region. So there is just one major highway. So if we have to actually utilize the areas, like if you can see even in central Oman, there are terrains which can be utilized for setting off of PV plants, then it's not quite possible because they're not accessible by roads. And even again, if we consider the radiation, then the central Oman doesn't receive very high annual solar radiations, so it's not a good candidate for setting up solar panels. So after considering all these criteria, we can make this map. So they have made this map, which is which considers all criteria and gives us the actual suitable areas for setting up PV solar plants. So you can see that majority of the area is non-suitable, and after the calculation they said that around 0.5% of the entire land Oman is highly suitable, but that doesn't directly mean that other land is not suitable for solar panel or for solar for using for harnessing solar energy. So the term highly suitable is kind of an ideal condition which would give us the maximum input and maximum efficiency of converting solar energy into electricity, but we can equally exploit the moderate suitable areas as well. So again, we can see that majority of the country falls under the moderate suitable area. So that can be equally used to generate electricity by using technologies which have higher efficiency of solar harnessing. Then this is this. Then we can use this formula to actually calculate the output of the solar power. So considering the first three factors, so that is the GP. So considering we have to calculate the GP, that is generation potential in terms of gigawatt hour per year. So the variables, that is SRCA and AF, that is solar radiation calculate, and the suitable land calculated suitable land, and the area factors are the uh, criteria which we have incorporated through which they have incorporated using the GIS model, and whereas the N efficiency is actually the efficiency of the technology employed. For example, CSP technologies are highly efficient compared to the conventional photovoltaic cells. So SR will be the annual solar radiation, the first map which we have discussed. Second is the suitable land, so that is based on the slope and terrain, and the area factor is the accessibility factor compared to the road infrastructure in the Oman. Then at the end, they have concluded that Oman being a tropical country in a Mediterranean country which receives very high solar radiation can be utilized to generate electricity, and the 0.5% of the land area actually demonstrates the ideal suitability for PV farm implementation. And it is seen that if the entire suitable land which is available in Oman is exploited or utilized for the say PV farms, then they can actually generate 45 times the actual demand for the in Oman. So basically, we need not exploit the entire potential. If even if 2% of the entire potential is put to use, then we can fulfill the energy demand of the entire country. So that was the conclusion. Thank you.